Good afternoon, friends. So, in the yesterday's lecture, we have introduced the definition of the we have introduced our third chapter, that is surface. So, in the calculus on the surface means what we are going to study all the properties of surfaces. Rather, we are going to study in this only the smooth surfaces. Okay. So, with the help of the calculus, we are going to study those properties of surfaces, just like how what is just like in the finite apparatus we have studied what is radius of curvature, what is a curvature, what is velocity of the curve, what is a turning, what is twisting, what is a rate of twisting. So in this way we are going to see the properties of surfaces with the help of calculus. So mostly we are going to study the smooth surfaces. Up to now in the mathematics we haven't defined what is surface. So in the differential geometry we will define the surface. Okay, here in this chapter we are going to study the cylinders, spheres. Later on you will able to understand what is a surface and all. So just now we are going to study first what is a regular mapping. What is a regular mapping? We have studied that a mapping F is said to be regular if the rank of the Jacobian matrix is equal to dimension of a dome. And I have shared you one lecture of Jacobian matrix also, how it is introduced. Before that, you should know what is explicit and implicit function. So, what is a rank of a matrix? A matrix is said to be of rank R if and only if it contains a non-zero determinant of order R. And every determinant of order R plus 1 is 0. This also we have studied in the last lecture, that if suppose you are having any matrix, suppose it is 5 cross 5 matrix, and if you get determinant of a matrix 4 cross 4 whose determinant is not equal to 0. But if you see the determinant of order 5 cross 5, if it is equal to 0, then you can say the rank of a matrix is 4. We have, now let us go for the next one. Here we have introduced the definition of the coordinate patch. So what is a coordinate match? D be the open subset of R2, then the mapping X from D to E3. If X is going to satisfy the condition of being X is 1 1 and X is regular, then X is called a coordinate patch. So in the very easy way, suppose you have a rubber sheet and you apply a mapping of, or you apply a function that you are going to spread it, or you are going to apply some function in such a way that the rubber sheet, if you stretch that function, that X we are going to apply is a stretching. After stretching a rubber sheet, you can convert it in the form of a 3D object. You can convert that rectangular rubber sheet in the form of the half sphere or any 3D object. So in the very similar way, if you तुम्ही एक पत्र घेतला, त्याला बळवल्यानंतर त्याला एक दुसरा शेप मध्ये कन्वर्ट केल्यानंतर त्याला आपण एक 3D ऑब्जेक्ट मध्ये बघू शकतो. Just like x of d, here we can see is a x of d is our image. Okay, mapping x, after applying x on d, we are getting the image is x of d, which is a in 3D space. Okay, so just resemble the definition of our curve alpha. What was our definition of a curve alpha? If you remember, a curve alpha was a function from, what was this? Curve alpha is a function from open interval I to E3 space, right? Open interval I to E3 space. Right. So this was a curve alpha was a function from open interval I to E3 space. But now the open interval I, which is a subset of R, is replaced by open set D, which is a subset of E2. So here we have moved from a real line to a R2 plane. Okay. 2D plane. So here again, if you see, you can remember, I hope you remember that a curve alpha is said to be regular if alpha dash of t is not equal to 0. Here also, what is the definition of a coordinate patch? First is x is 1, 1, second x is regular. What is the meaning of regularity for the curve alpha? Alpha dash of t not equal to 0. Okay. So what here you can see the curve alpha is said to be regular if alpha dash of t not equal to 0. That is, we get one single independent vector, that is alpha dash of t. If alpha dash of t not equal to 0, then we say that the curve is regular. In the very similar way, if x is a function of two variables, let's say u and v, you can see here, instead of saying x and y axis, we are having u and v axis. So x is a function of two variable u and v, and resultant we are getting in terms of that is we will get again in terms of u and v, but it is in 3D object. That is, it may be just like u square uv v square, or it is 2u sine v. That is a 3D object, or we will get one vector just like in the terms of u and v. So here just we have to differentiate x with respect to u and v. So what will be xu cross xv? If it is not equal to 0, then it will give you that this is a regularity condition. Later on in the next 2 or 3 lecture, we will study that rank of a Jacobian matrix is equal to 2 is called a regularity condition. Just now we have seen. And here xu cross xv not equal to 0 is also regularity condition. So after all, after that some 2 or 3 lecture, we will prove that xu cross xv not equal to 0 is a regularity conditions. Okay. So this is what a coordinate patch. Okay, now let us discuss what is a proper patch. First, it should be a coordinate patch. X is a mapping from D to E3 is a proper patch if the inverse function x inverse x of D to D is a continuous. If inverse function is continuous, then it is called a proper patch. Now one may have a question how inverse function is going to exist. So here if you see x is 1 1, x is 1 1, and it is already we are discussing everything in E3 space, that is our discussion is on E3 space, so it is finite dimensional. So 1 1 condition ensures the onto. So it directly shows that the inverse function exists. So a mapping x, if you see, is a mapping from D to E3. So everything whatever we are discussing in the differential geometry is restricted to our 3D space or E3 space, Euclidean space. So this 1 1 condition ensures that it is onto, and hence we can say that an inverse function exists. So now we have to show that that inverse function, whatever it is existing, it should be continuous. Then we say that it is a proper patch. Now one may have a question how the inverse function is going to define. Now if you see the mapping x is a mapping from D to E3, but what is image whatever we are getting x of d is only a subset of E3, it is not a whole E3. So if it is not a whole E3, then we can define a mapping, the inverse mapping you can define it as just like a mapping it will be from, so inverse mapping I can define from here to here, so this will be x inverse. Okay, so the x inverse will be a mapping from x of d to d, correct? Because we don't need a whole E3 space to study the inverse mapping, because x is a mapping from d to E3. So what will be x of d? It will be range is always a subset of d. So a range is subset of a codomain. So hence we can say we can define a mapping x inverse from x of d to d. So now we can have this inverse mapping from x of d to d. So this inverse mapping, we have to show that it is a continuous. Okay, so let us show how it will be continuous. Okay, in the next examples, we will see what is a coordinate patch and proper match. Okay, so here it is shown that x inverse must be a continuous map. So what is the meaning of continuity? If we want to show any mapping x inverse is a continuous. Now if you see a mapping x is a mapping from D to E3, but what is x inverse? X inverse is a mapping from x of D to D. That is, it is a mapping from just like E3 to E2 space, because D is a subset of E2 and x of D is a subset of E3 space. Correct? So here you can now see that x inverse we have to show it is a continuous function. Now let us go for one example so that the idea will be clear. What is given in the example, let x be a mapping from D to E3 where x of u v because x D is a subset of E3 and D is a subset of E2, so hence we can write x u v is equal to u square u v v square. Okay, what is D we have provided? It is any subset of a E2 space. So, what is the condition for being a subset of E2 space? U and V is strictly greater than 0. So, all the whatever we are going to study, that is D, which is a subset of E2, that is, it will not be equal to 0. So, just we are going to take all the points which are non-zero. U and V strictly greater than 0. Okay. Just like if you can see, we'll have D as, so this is what our U and V, this is U and V, so we are going to just take all the points here, that is U and V both are strictly greater than 0. Okay, we are not going to take any points here, or if it is equal to 0, U and V are equal to 0. Simply we are restricted to this plane. Okay, we are not interested in this part. Okay. If you're confusing, let me extend this. So this is what our UV plane or XY plane. So we are only restricted for this one. Okay. So let us study what is a mapping X. So what is a mapping X? X of UV is equal to U square UV V square. To prove X is a coordinate patch, we have to prove first it is a 1 1. Now one may have a question. Why to study 1 1? Because if you see here, the 1 1 condition ensures that your plane is not cut. That means suppose you have taken any rubber sheet and you have applied a mapping in such a way that if suppose you have cut the rubber sheet and then you have converted it to a one 3D object. But if suppose you go back, okay, we are not going to get that cut part. So this condition of 1 1 ensures that for a mapping X, it shows that it avoids the cutting of a plane. Okay, so here you can see this. The condition of regularity ensures that the curve is smooth, and the condition of axis being 1 1 avoids the cutting of the surface. That is, whatever the x of t we are getting, it will be a smooth three-dimensional subset of a E3 space. Correct? So whatever the image we are going to get, it will be a continuous one. So let us study what is our mapping X is given to us as U square V square U square UV V square. Okay, so let us see whether X is 1 1. Okay, so therefore let us first, if we want to consider X is 1 1, let us check the images are equal. X of u1 v1 is equal to x of u2 v2, or you can check x of uv is equal to u1 v1. Later on we have to prove u is equal to u1, v is equal to v1. Okay, so just taking by the our mapping x of uv, u square uv v square. So here also u square uv v square, here also u1 square u1 v1 v1 square. So just by having a coordinate wise equality, you can have this u square u1 square is equal to uv uv is equal to u1 v1, v square is equal to v1 square. So hence from this you can say, by taking the square root, you can say that u is equal to plus or minus u1. But if you see our domain D, what is a domain D? It is strictly greater than 0. So we cannot take the negative value. So hence we can say u is equal to u1 and v is equal to v1. Okay. So u and v both are greater than 0. Hence we cannot take the negative values, and hence we can say that now x is 1 1. So how to prove x is regular? First you have to say x is equal to x1 x2 x3. We are going to take them, we are going to name this u square uv uv square as a sum x1 x2 and x3. So now we have to find out now Jacobian matrix. Now if we already know that what is a Jacobian matrix, how to find out the Jacobian matrix, you can find out like this also, or you can keep u as it is and vary x. Okay, just like that. So dou x1 by dou u, dou x2 by dou u, just you have to take a derivative of x1 with respect to u, x2 with respect to u, x3 with respect to u. And then again x1 derivative of x1, x2, x3 with respect to v. After taking a derivative of x1 with respect to u is 2u, x2 with respect to u is v, x3 with respect to u. Because v is independent variable, so hence we can differentiate with respect to u. The resultant will be 0. Similarly, derivative of x1 with respect to v will be 0. Again, derivative of x2 with respect to v will be u as it is constant. So now x3 with respect to v will be 2u. Now if you observe this Jacobian matrix, if u and v both are strictly greater than 0, the rank of any 2 cross 2 matrix, if you take any 2 cross 2 matrix, and if you find out the rank, or if you find out the determinant of any 2 cross 2 matrix, it is always non-zero, right? We can see that 2u so hence here we can say 2u v u 0 u, so you can say 2u square, but u is strictly not equal to 0, so hence u is strictly greater than 0, hence you can say this is the rank of the Jacobian matrix is equal to 2. By definition, hence we can say that x is a regular mapping. So we can say x is a coordinate patch. Now we want to prove that x is a inverse function is also continuous, so that in all total x is 1 1, x is 1, x is regular, so x inverse is a continuous function. In all combinedly all these three, we can say x is a proper patch. First we have proved the coordinate patch. To prove the inverse function is continuous, first we have to define the inverse function. Now instead of defining x inverse, let us name this as y is a function from x of d to d. Just now we have defined in the last one, that is it will be a function from x of d to d. Okay, so let us write this as y of xyz is equal to some root x or root z. Now why this is like this, so you can see here what we have, x of u is equal to, what we have x of uv, let me write in this, in the definition, in the example itself, x of uv we have provided as u square v square, sorry, u square uv v square. Now we have to define a mapping x inverse. So instead of defining a mapping x inverse, we have defined it as y of xyz, as it is a mapping from x of d, and x of d is a subset of E3, hence we have to take the three elements, that is x, y, z. Instead of defining x of uv, we have to take the three variable x, y and z. So y of x, y, z is equal to, we have to find something. Okay, so for that we have to first write down, what you will write down is x of uv is equals to okay, first we have to write down xyz, y of xyz is equal to some uh, something which is in 2D plane or which is a subset of a 2D plane. Okay, it is in 3 variable. Now here whatever the image we are getting, it is in terms of 2 variable, correct? So for defining this, first we must concentrate what we have already. What we have already, it is u square uv v square, correct? So for that I can name this as x is nothing but u square. Okay, and next what is the second variable we have? V. We can name this v as a that is v square as a y, right? So what I get so what will be the value of x? X is, so u, what will be the value of u is root x. What will be the value of v? Will be root y. So the things we have written here is y of xyz is equals to now uv, right? So here we are having the three variables xyz. What we have in the t, we have other only two variables, that is u and v. So y of xyz is equal to, first you have to write down uv. Okay, and how you are going to calculate the value of uv? Here you have to write down it as, okay, to understand this, we will write down it as u comma v, correct? Because we are now we have to find out the inverse mapping, correct? Y of xyz is equal to uv, but how we are going to find out the value of u and v? Because we have defined the inverse function. So for that you have to go back. Okay, first you have to check what is a function we have defined. It is u square uv v square. So for that, now just we have to rename this. Okay, here we have defined uv. Okay, and here what we have, this we have to rename it as, we have to write it as just like x y z. Okay, let me write here x comma y comma z, correct? So now what will be the value of x is u square, value of y value of y will be uv, and z is v square, but we want only in terms of u and v. So what will be the variables now? So here you can say what is the value of u will be under root x, what will be the value of v will be under root z. So what is the second term we are getting? U into v, that is y is equals to under root xz. So hence we can now write x composite y will, of xyz will be x composite. What is y of xyz? We have it is nothing but root x root z. So hence now you can say what will be x root z. So what is the mapping? X is, x of uv is u square uv v square. So what is the square of this first is x, square of second is z, and what is the middle term? Product of these two, root x into root z, is nothing but your y. So similarly you can check for y composite x. So what will be y composite x? Y of x of uv. What is x of uv? We have u square uv v square. What is y of xyz? What is the y of xyz? We have here. So first term, root of first term. What is the root of first term? U square is u. Second term y is as it is. So what is third term? Z under root of z. Okay, what is the third term? V square. What is under root of v square is v. And hence you can see here xy of xyz is, we are getting xyz, y composite x is again uv. So we can say x composite y is equal to y composite x, right? And x composite y is giving xyz as xyz itself. So you can say x composite y is as an identity map, as well as y composite x is a identity map. So we can say y is equal to x inverse. So we have proved that x inverse is nothing but y. Since a coordinate function, you can see root x, root z, these are nothing but your real valued function under root of x on the condition u and v are greater than 0. Hence, you can say x inverse is continuous. X inverse will be continuous only if its coordinate functions are continuous. Okay, what is x inverse of x, y, z? We write it as root x, root z, right? So here instead of writing y, we have defined. So what I will write instead of y, here I have to write down x inverse. So what will be x inverse of x, y, z? It is under root x, under root z. So under root x, under root z, both are continuous functions. So hence x inverse will be a continuous function. How you are going to verify the function is continuous? You have to check its coordinates. So if coordinates are continuous, then you can say x inverse is a continuous. It follows that x inverse is continuous. So from 1 to 3, you can say that x is a proper patch. So in the very similar way, in the next lecture, we will define the surface. Okay, thank you.